Hi, I'm Kwang Moo Yi. I'm an assistant professor at the University of British Columbia, and I work at the field of computer vision and machine learning. And today, what I'm going to talk about is how we learn errors so that we can optimize through that with deep network to get some accurate sports field registration. So this is a joint work with SportLogic, and we presented this at RAFI 2020, and this was work done while I was at University of Victoria. So the problem that we are interested in this work is the problem of registering the view that you see, the image that you see here, to a sports field model like the one that you see over there, in a way that we could actually relate between the two. So for example, the view that you see up here is corresponding to the tilted view you see on the right. And once we are able to do that, we can do fun stuff. So for example, we could locate where the players are on top of a tabletop view so that we could do some strategic analysis. And we could also do the other way around where we place some virtual objects on the sports field that are going to now be augmented into the actual live view. So all these require you precisely knowing the relationship between the images right over there. In a nutshell, it's something like this. So we have the broadcast view, and what we want to do is we want to figure out the camera pose so that we can actually, for example, draw the lines on these soccer field lines, which would only be possible if we were to actually know the camera pose. And that seems very easy, but it's not actually. So for example, you see on the left here, which is the results from a deep neural network trained to localize the camera with respect to the image by just looking at the image. And it shouldn't be too hard if you think about it, because soccer fields have a lot of standards. And it's also very obviously shaped in terms of lines. But in fact, it's not. As you see on the circle right over here, you see that the alignment is quite bad. Whereas, sort of a spoiler, that if you do this properly with our method, you can get the results as you see on the right. So before we detail our method, the first thing that I want to do is go over and understand why this is so hard. Because without understanding the core of the problem, it's really hard to solve. And understanding the core of the problem, I need to talk a little bit about math, but don't worry too much because it's going to be confined to linear algebra. You don't need to know anything about deep learning theory here. So a little bit of complicated equation here in terms of matrix, but don't worry too much and you don't have to understand the whole thing. I just wanted to point here that this equation is what governs how we estimate homography. So the matrix on the left is composed of coordinates from one image and the coordinates from another image. So in a sort of a way that they form a relationship that makes sense physically. Like for example, light can't bend, right? And then on the right, you have the parameters of the homography matrix in a vector form. And then the equation becomes that when you multiply these two, you should result in 0. In a nutshell, what this says is that light travels from one image to the other, and they should correspond to the same physical point. And this is how you describe that in terms of math. Or simply put, it's looking something like this. You have A matrix, which is now corresponding to the relationship between two images, and H, which is a parameter of the homography matrix or the camera pose that we define. And then we basically say when you multiply the two, you need to go to 0. Now, this is how a system is defined, and it's a linear system. And all we need to do is now find H that satisfies this equation, then now you know the camera pose. Now, that's a simple system. And now I'm going to talk a little bit about why this might be potentially harmful to solve with deep learning. Finding H here just corresponds to you solving the system using something called the singular value decomposition. And there's a little bit of problem when you solve this equation, which is that you're actually aiming for the vector corresponding to the smallest singular value. And the problem with this is that this is going to be an ill-conditioned problem. When you try to change a little bit on your data or even on how things change in your output, it's going to be amplified because we are looking for the smallest singular value. And then basically, you're going to try to estimate how H star here, which is the H that minimizes this equation, changes according to how you change A. That's basically what you're trying to do with deep learning methods that learn to directly regress the parameters of H, which is the common way to solve this. So mathematically, you're doing something like this. You have a deep network, let's say we write that as a function f with parameters phi, and then you put in a, and then you want to have this deep network spit out the correct answer that corresponds to what you have above. Now, well, we all know deep networks are capable of doing black box estimation, right? So you have a bunch of your inputs and outputs all defined, and then you push them all through, and that's how you train a deep network. Well, in this case, you're going to have some issues because small changes in A is going to cause large changes in H star, and vice versa. So your learning is going to try to imitate what is very tricky to do in a single for loop. So this is potentially why deep learning had trouble actually doing this. And slightly off topic, but we do have a paper in 2020 that looks into this phenomenon in more detail. So now we know the problem. We know the problem is that we're actually trying to learn something that is really tricky to learn. We're going to have to learn how to change large amounts with small changes, or even large changes with small amounts. So what we're going to try to do instead in our work is to not do that at all. We're not going to ask the network to solve our equation. What we're going to try to do is something else. What we're going to do is to learn the error. Instead of learning to imitate the optimization process or the solving process, which is directly spitting out H star, what we're going to do is we're going to just have a network, let's say, call that G, that takes in our current guess and the input conditions, and then just say, we're going to estimate how good we are doing. For example, given a certain H, we're going to say, how good is your H by, for example, in the left, that's the error metric that the SVD was minimizing, or even some other better error metric could go there. So basically what we're going to try to do is, given a hypothesis, we're going to learn to evaluate how good that hypothesis is, which means that we can now use our neural network that is differentiable and differentiate the outcome with respect to H here, which would then allow us to enhance our hypothesis so that the estimated error gets smaller. So now recap. The traditional method of solving this homography estimation problem requires that you go through a solving of an ill-conditioned system. Now, the network that regresses the registration parameters are essentially learning a function that imitates this process, and that's going to be hard because you are going to have to cope with the ill-conditioned nature, which is not great. So what we can do instead is to learn the estimated error. And this means that we don't go through this SVD process at all. We just learn a different quantity, and we use the differentiability of neural networks to then enhance our results instead of getting a direct solution. So that's the core idea. Now, how we implement this is a little bit different. So this is our big pipeline. It has multiple components in. You see that you have the deep network, well, actually two deep networks over here. It's a little bit daunting, but let me explain each component one by one. So the first part over here on the left is nothing but a typical pose estimation network. So we do start from a certain hypothesis, which is given by a neural network. So this is going to be the wrong result that you saw before at the first slide. But we're going to now try to go and update this so that it gets better. So our innovation is actually the right-hand side, which is where we learn to evaluate the hypothesis. what we do is we get an H here, which is a hypothesized pose. And then what we do is we use the soccer field template that we have to warp that into the view. And then we use those warped view and the input image and pass it to a deep neural network, G, which is now going to tell us how good we are doing. And then at the end, once we have that hypothesis, what we can do is we can differentiate through the whole pipeline all the way from the error that we have to the input hypothesis. And now we have gradient for the hypothesis that tells us which direction we have to move in order for the error to get lower so that our results get better. Well, that's it. That's how we actually implement this. And there are some details in actually making it work, and details are important. For example, here we parameterize the homography not using the 9 numbers as a raw matrix, but rather we parameterize it using 4 points in the view. So we call these control points, and this idea was not only used by us, but it's a common idea that is used when you represent 3D poses. And of course, that's not all we do. We train with data augmentations because we're training to figure out how much we're off in terms of hypothesis. What we actually do is we look at the data and then we perturb these a little bit, which then creates twisted data, which is not too far off from real data. And then we use them as our training set. And we also, on top, add some artificial shadows on top of the soccer fields because it turns out that's something that happens quite often. So we put them in so that the network learns that this is not important and irrelevant of the task that we are trying to solve. And as a result, one of our networks that we've shown, or the network that we're going to show with the soccer field estimation, is trained with as little as 209 images, and it still works. So here's an example of how optimization actually enhances the pose. So right now, this red pose that we see here is actually a pose given by a deep neural network, or rather a feed-forward deep neural network that estimates camera relationship or the homography matrix in one shot. And what I'm going to do now is use our trained network that estimates the error, which we call error network, and we're going to differentiate the estimated error with respect to the homography parameters, and we're going to move the homography parameters around so that the estimated error gets lower. And this is what happens. You see that the error gets adapted on and on and on, and then now it becomes quite accurate. And the difference is quite huge. If you look at the feed-forward results, you see that they're quite off. Whereas when you optimize so that the estimated error gets lower, you get quite good results as shown here. And the reason we can actually do that is because the estimated error actually is quite close to what we have for the real error if you were to measure it. So here, what I show you is the estimated error surface on the left. So we move the homography a little bit with small translations, and we measure how the error network is saying how good we're doing. And on the right is the actual ground truth error surface. Well, the shapes are not exactly identical because we can't really expect the error network to do perfectly. But one thing very important here is that it did learn the concept of which is better. You see that the minimum point in the estimated error surface on the left is the same as the ground truth one. And it does have a decreasing shape as you go closer and closer to the actual solution in the center. So here are some qualitative results. So this is a video demonstrating how our method and a typical feed-forward method, as you see here, performs like. And of course, with our method, enhancing the registration results, you get much better results. For example, as shown here, while the feed-forward method on the left does have a lot of errors, ours are quite snappy to the actual soccer field line that you're seeing. And what is actually impressive is that our results that you see here have no notion of any temporal smoothing. So it's the raw result that you get frame by frame and they're quite accurate. So with some post-processing, you can get even further, I would assume. And of course, more results, screenshots, all of these highlights are in the paper, and also the video is online on YouTube, I believe, so you can have a look at that as well. So of course, qualitative doesn't tell the whole story. So we have an extensive quantitative study in the paper as well. I won't go too much into the details, but in a nutshell, our method works quite well. And more numbers as well in terms of variance of what you can do with our method, for example, which error metric is the best to regress towards. We also have those results as well. So if you're interested, do have a look in the paper for more details. Now, I've been talking a lot about sports fields, but this method is not really that restricted to sports analytics only. We can also use this for other general problems as long as it involves, for example, least square fits or involves SVD. So here's another example, or rather a toy problem that involves doing SVD. So what you do here is, given these images you see on the top, which is like noisy images with random circles and a single line, we train a deep network to estimate the parameters of this line by looking at the image. It's quite similar to the sports field registration problem or the camera pose problem, but it's a much more simplified version of it. And you see that even for this simple problem, with unlimited data, because this is synthetic data, we create unlimited data and let the network train forever, you still get this result with the feed-forward strategy. You see, it's not as accurate. And if you use our technique, which again evaluates how good you're doing in terms of estimating these line equations, you get quite good results. You get significantly better results, in fact, especially in terms of the median error. So our research stopped here, but I would suggest that you go and try this method for other applications as well. Except one catch here is if you want to use it for commercial purposes, you might want to consult Sport Logic because this algorithm is patented. So in summary, what we did is that we first saw that the registration of an image traditionally requires solving an ill conditioned system, meaning that you have to find the singular vector that corresponds to the smallest singular value of a matrix that is singular. So this is really not a nice problem to deal with. And you're actually asking a deep network to imitate the behaviors of finding a solution to that problem. And that's going to be hard. And therefore, we propose an alternative where you could learn to estimate an error or to estimate how far you are off from the final objective given a hypothesis. So given a pose parameter or given a certain H vector, how good are we doing? And by doing so, you're able to then differentiate the quality of your error with respect to this H or the pose parameter, then you can enhance it on and on iteratively. And of course, that leads to better results as you've seen before. So that's it for my talk today. Thank you for your attention. And these are the actual people behind this work. And we release all our code and all the things that are necessary to reproduce the experiments in this GitHub. So do check it out if you're interested. And again, if you have any questions that I cannot answer during the QA period, please feel free to email me as well. Thank you again.